All right, so let's get started with today's lecture. Today is day two of this 10-day agent bootcamp. And the main topic which we are going to cover today is what exactly is a large language model. The reason we are covering this topic is, if you remember from last lecture, we saw that LLMs or large language models are the brain of how agents actually operate. And without understanding LLMs, understanding agents is impossible. So that's the main goal of today's lecture. After today's lecture, I hope all of you have an intuitive understanding of what large language models are. Similar to what we did for agents, we are going to look at large language models from the first principles. And I'll encourage all of you to come up with your own definition and understanding of LLMs so that you feel as though things are intuitive. So one of my goals of these lectures is to also make sure that these terminologies are not just something new to you, but you find them intuitive and easy to explain to anyone else. Before we actually get started, let's first do a quick recap of the previous lecture. For those of you who are enrolled in the Pro plan, I've shared this Substack article with all of you now. We'll be making it private for our Discord community, but I've opened it up here so that I can recap the previous lecture. So we started by defining agents, right? And our first definition was an agent is something which takes you from point A to point B and adds value to your life. That value can be time as well as money. But then we saw that cars, planes, and so many other machines can also do this. So we needed to augment the definition of agents. Then we saw that agents not only take you from point number A to point number B, but they can also help you plan and take decisions. But even self-driving cars can plan and make decisions, right? So we needed to further augment our definition. Then we said that agents also have access to tools. What are these tools? These tools can be Google search engine, the ability to access websites and read what's written on the website, the ability to go to payment gateways and make the payment, the ability to draft emails. All of these are tools. So agents have access to tools. And then finally, we saw that the reason we are having this bootcamp in 2025 is because 2017 was the year where the transformer architecture came into existence that completely changed the field of language modeling. And language models became massively better at understanding and responding to human language. So agents use LLMs for planning, reasoning, and decision making. That's why I call LLMs as the brain of agents. So then we had to finally modify our definition by saying that agents also interact with the external environment and they have memory. So in this one figure, I have encapsulated our entire understanding of the previous lecture. And let me define agents finally once and for all. So agents take you from point A to point B and they add value to your life. They do this because they have access to tools. Using those tools, agents can plan and take decisions. They can also interact with the environment and they have memory. And the foundation of all of this, the foundation of planning, decision making, reasoning is a large language model. So I hope that sets up the stage for today's lecture, because if LLMs are indeed the foundations of agents, then we need to understand what exactly LLMs are. And I plan to take you beyond the usual way of understanding LLMs, right? All of us interact with ChatGPT now. But I plan to kind of take a look behind the curtains and really understand LLMs from the first principles. So let's take an example, and I want all of you to be wearing your thinking hat at the moment and try to answer this question, which I'm going to ask all of you. So imagine that you are an alien, okay, but you are a very smart alien and you have access to all the material which has been published. You have access to books, blog, literally everything, and you also know mathematics, you can think, etc. But you don't know anything about language. And here's your task. I will give you an incomplete sentence, and your task is to take the incomplete sentence and you have to predict the next word. That's it. You have to take an incomplete sentence and predict the next word. So forget everything you know about LLMs at the moment, or everything you might have learned about LLMs. Just try to answer this question. You are an alien who is super smart and who has access to books, blogs, and I give you this sentence. Let's say your effort will take you, and as this smart alien, I want you to complete this sentence. In fact, I want you to answer what would be the next word after this sentence. How will you do this? Again, think from first principles, right? How will you do this? So I can see some answers in the chat based on previous occurrences in textbooks. What about others? Word which have the highest probability in articles and blogs. There is some answer that without language we can't. I will look into my context that I have from the material, right? So one very popular answer or one very intuitive way to think about this is what many people have caught on to the correct idea, that we will go through all of our textbooks and we'll try to see where all these sentences or these word actually comes. And then let's say this same occurrence, your effort will take you, comes 500 times. We'll see out of these 500 times, what's the word which has the highest probability of coming next. So what's the word with the highest probability? So if I was the alien, I would have done this. I would have looked at all the data which I have, and let's say this sentence comes 500 times. I would look at those 500 sentences and I would have seen what comes next. And I would have chosen the word which comes the most number of times, or I would have chosen the word which comes the most frequently. Okay, that's how you predict the next word. But what about the word after that, and the word after that, and the word after that? What if you want to predict an entire sentence? This is where the problem comes, because if you look at the English language, and let's say we say that the vocabulary has 40,000 words, right? If you want to predict one word into the future, there are 40,000 options. If you want to predict two words into the future with such a probabilistic approach, there are 40,000 multiplied by 40,000 options. If you want to predict three words into the future, there are 40,000 multiplied by 40,000 multiplied by 40,000 options. That's around 1.6 trillion options. And the funny thing is that if you want to predict 20 words in the future, then it will be 40,000 multiplied by 40,000 multiplied by dot 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 20 times. And that's more options than the number of particles in the universe. So this just becomes an impossible problem to solve, right? Through just a probabilistic approach, that I cannot look at my past data and predict a full sentence. It's just impossible to do. Another issue is that what if the given sentence does not come anywhere in your past data? Then what are you going to do? Then it would be impossible to predict the next word. So what do humans do in situations like this? Humans do a very simple thing, right? Let's say, I'm sure all of you are aware of this Leaning Tower experiment, right? Leaning Tower of Pisa experiment. So let's say you are the scientist and you drop some material from the top of the tower and you want to find the time which it takes for the material to reach the ground. And you do it for 10, 15, 20 number of trials and you note down the readings. What do you do after this point? Once you have some data, there is one particular thing which all physicists have done. Once you have data, what's that thing? What do you do after you get data? Even Newton, let's say, you have the data of how an object moves, right? What do you do with all of this data? So already we can see some answers in the chat that you try to find patterns in the data, right? And what does it mean trying to find patterns in the data? It means creating a model. We create a model. We create a model for how much time it takes for a ball which is dropped here to reach the ground. So let's say that time of descent is square root of 2 into height divided by the gravity, something like that. That's a model, right? Um, so models can be very powerful because what's essentially a model? You have an input, the input goes to the model, and you get an output. So what if we do something similar in this case also? In this case, what if I take my given set of words, I have my given set of words, I'll pass it into a model, and what I want as the prediction is my next token. So what if we could create a model which accepts a given set of words as an input? So this set of words, let's say this set of words or any set of words, these set of words will be given as an input to the model, and the model's job would be to predict the next token. That is exactly what people tried to do. Since we could not predict the next token by normal thinking, by statistical reasoning, then we turn towards models. And such a model, this model which takes an input sequence of words and predicts the next token, that's called as a large language model. Okay, forget the word large for a moment. That's called as a language model. Now let's understand why it's called a large language model. If you take y equal to ax plus b, how many parameters are there in this model? Can you answer in the chat? A simple straight line. Simple straight line has two parameters, correct? If you go to quadratic, there are three parameters. Now I'm going to make a statement which should be extremely shocking. Large language models have billions of parameters. People who have been in this field would now think that this is quite normal. But again, go back to what we have studied in school, right? We studied 2 parameters, 3 parameters, 10 parameters, that's fine. But what if I suddenly tell you that language models have billions of parameters? This is impossible to understand. And I just want all of you to appreciate the scale of this. It's already quite hard to deal with, like all of us can visualize a two-dimensional surface, right? But we cannot visualize a four-dimensional surface. It's impossible. Now I'm telling you to look at models which have billions of parameters. That's that's something which cannot even fit in our minds. Because let's say, to give an analogy, let's say this is India's map, right? And these are all the people, more than a billion people, right? So each of these persons, if these are a parameter, if each person is a parameter, even still there would be 100 such countries which need to be created to have as many parameters as language models have. And every parameter will have certain value which is optimized so that we can predict the next token. So when we say large, when we attach a word large, the reason this word is attached is because large does not mean 10 or 100 or 1000. It means millions and billions of parameter. That's what large language models are. Large language models help you predict the next token. Large language models help you predict the next token given a set of words, and they have millions or billions of parameters. The advantage of models again is that, let's say if you had this data, if you have this data and you make a straight line through it, the advantage of models is that if I give you any other input which is not present in my data, I can still predict an output for it. So similarly, even if I give you a set of words which are not in my data set, my language model will still predict the next token. That's another advantage of using models. So that's the first principles approach of language modeling. And still, the question which all of you should be asking is that if we are predicting the next token, why is it called a language model? It should be called a next token prediction model, right? Why is it called a language model? We'll come to that in a moment. But for now, just keep this definition in mind, that language models predict the next token. And when we say large, they are really large in terms of the number of parameters which they contain. All right. So now one thing which I want to ask all of you is, let's say when I ask uh, get me the code or get me, let's say, recommendations for books to read this year. If I go to ChatGPT and if I ask something like this, there are next tokens which are predicted, right? As I told you, language model predicts the next token. So given a set of input tokens, we have this as the next token, then we have the token after that, then we have the token after that, then we have the token after that. Let me ask you the question, is ChatGPT or does ChatGPT, is it fully confident in making these predictions? So put in another way, is this a deterministic prediction or is this a probabilistic prediction? So we can see in the chat that people have answered it's a probabilistic prediction, right? So indeed, we see these tokens which are predicted, but what a language model actually does is that as it predicts the next token, it has, it predicts the probability actually, or it chooses the token which it thinks has the maximum chance of being the next token. So we are now just going to do a small activity in Google Colab. Um, Before we move to Google Colab, I want to ask how many of you have access to their own OpenAI API key? We would need an API key for the rest of this duration of the bootcamp. So I'm just going to show you the process of creating your own API key. I'm sure many of you already know this, but you have to go to openai.com, then you have to log in. So here I'm logging in with Google right now. So you have to log in here and then you have to go to settings. When you go to settings, you have to go to API keys section over here. And then you have to click on create new secret key. And when you click on, let's say, so I type a name Agents Bootcamp and then I create my secret key. So don't share this with anyone. This will be, you will get some free credits, I believe, but after that, it will be charged. So in this bootcamp, we won't be needing a huge amount of API key usage, but it will be needed. So can you all mention how many of you does have API, OpenAI API key right now, or how many of you can immediately create one? So make sure that don't share your keys with anyone. So I'm also going to delete my key over here once I share this notebook with all of you. So if you don't have a key, you can go to OpenAI like I went right now, and you can create this key. Um, so if you go to platform.openai.com, you can go to the API keys section, go to settings, go to API keys. You can create new secret key and you can copy it. In any case, if you don't have a key, I'll share this Google Colab notebook with all of you. So then you can experiment with this later. But so what I'm going to demonstrate here right now is that you just install this OpenAI package. And then what we are going to do is that we are going to see the probabilities of the next tokens which are predicted. So the input sentence which we are going to have is after years of hard work, your effort will take you, and then we are going to predict the next token. Um, Let me just share this code file with all of you right now. Okay, before I do that, let me show you. So see, this is what's actually happening in the backend. When you type this on the chat GPT front end, when you type this sentence, you will see deterministic answers of the next tokens, right? But actually what's going on internally is that GPT thinks that, okay, all of these can be the next tokens. And here I've printed out the probabilities. So the probability that next token is going to be 2 is 80%, which is the highest. So then it will print out the next token to be equal to TO2. But there are all of these other tokens which might as well have been the next tokens, right? So I'm going to delete my API keys from here, and I'm going to share this now with all of you. Let me delete the API keys everywhere. So you can replace your actual API key over here. And for the purposes of this class, we will need API keys later also. So I encourage all of you to have API keys with you right now itself, so that later it won't be an issue. Okay, so I'm copying this link and I'm sharing it with all of you on the chat. You can run this file even after this lecture is over. But what I wanted to demonstrate here right now is that until now we saw that LLMs predict the next token, and this token is predicted in a probabilistic manner. The LLMs, when they predict the next token, they assign a set of probabilities and they choose that token which has the highest probability to become the next token. Okay, so this is the definition of what large language models are. Now let us peek a bit into how LLMs have become useful to us today, and we'll also see why they are called language models and not just next token prediction models. There is a question, do I have to buy their subscription from OpenAI? Yeah, if I believe you'll have to buy a subscription to, or at least add some balance to have API key access from the OpenAI dashboard. So key is still there in the collab notebook which I shared. Let me remove that. Anyways, this key which I have only has only like $0.5 or something balance. So yeah, so this is the first section of what I plan to cover today, that large language models. So let me write down the takeaway. LLMs are next token prediction engines. So LLMs, you can think of them as an engine which takes into account the input set of tokens, and then we predict the next token. Okay, now let's come a bit to the history of large language models and why they are called language models in the first place. Why do they need so many parameters? So here is the history of how it all started. The first paper which came out was 2017. This is attention is all you need. That's when they implemented the transformer architecture. Does anyone know the year in which the first GPT came out? What was the first GPT model which came out? So all of us know about GPT 3.5 chat GPT, right? But that's the product. When was the first GPT paper which came out? That's actually GPT-2. So GPT-2 paper, I believe, was submitted at the end of 2017 and it was made available in 2018. That's the GPT-2 paper. And it was titled Language Models are Unsupervised Multitask Learners. So GPT-2 had 1.5 billion parameters. Let me share this paper with all of you right now. This was the paper um, which introduced GPT-2 and it had 1.5 billion parameters. And this model could do a wide range of tasks, but it was still pretty small, right? So check this out. This was the parameter size in GPT-2. They had four parameters. They started with a 117 million parameter model and their largest parameter size was 1.5 billion. Then in 2020 came GPT-3. That's another huge advancement. And the reason I call this an advancement is because GPT-3, if you see the size graph which they have in this paper, GPT-3 came in a huge range of sizes, but their largest model was 175 billion parameter. And this was one of the first studies, I believe, which had this one figure, which was extremely important. It's this figure. What's actually shown in this figure is that the accuracy of the language model, which is on the y-axis, tremendously improves as you increase the number of parameters in the models. So if the parameters are small, so if you see the green graph, that's 1.3 billion parameters that has the lowest accuracy. As we go from green to orange to blue, the accuracy of the language model goes on increasing. So this figure showed people that it makes sense to go on increasing the number of parameters in a language model because the accuracy is increasing. Its performance on several language tasks just keep getting better. And then people were curious, right? Okay, 175 billion parameters achieves a good accuracy. What if I keep on pushing higher and higher and higher? So 2020, 175 billion parameter, and here people figured out that the size of the language model is actually proportional to the amount of tasks language model can do. So the higher the size, we can get better language models. Then 2022, GPT 3.5 came out, and that is what we know as ChatGPT, the product. But people in this field knew the powers of GPT from 2018 itself. It just got into the commercial space 4 years later when OpenAI converted their research into a product. That's when the whole world knew about this. Now people believe that GPT-4, their largest models, have more than 1 trillion parameters because they have just gotten so much better at reasoning. So if you look at the sizes itself, here is the GPT-2 size chart. They had 1.5 billion, right? That's the maximum. But there is this size scaling law in language models, which says that the amount of or the more the parameters you have, the better performance you get. So people just try to increase the number of parameters. So if you see, this figure was published in Nature. And if you look at year 2000, the largest model we had was 1 million. But as we go into the last decade, so if we look at 2020, at the start of 2020, we had models of about 100 million. And now we have reached around 1 trillion within a span of 5 years. So you see, this looks like linear, right? This looks like linear, but the y-axis is actually logarithmic. So this is actually an exponential increase in the computational or in the parameter size of large language models in the last decade. And they still continue to get bigger and bigger and bigger. Now, can someone tell me that why do we need so many parameters in a large language model? What's the reason? Why do we keep increasing the number of parameters? So I'm going to give you two explanations for this. One is an intuitive explanation and one is a technical explanation. So why do we need so many parameters? So let's see some answers in the chat. Accuracy and the performance improvement. But yeah, but why? Why do you think increasing parameters increases the performance? And when you say performance, what do you mean? Better contextualization, right? Takes into account all aspects, it can understand well. So, okay, more parameters leads to more performance. And when we say performance, we are saying that maybe language understanding or performance on language related tasks. Right? So I told you I'll give two explanations for this question. One is technical and one is the intuitive explanation. So let me start with the technical explanation first. There is something which is magical about language models, and that is the fact that language models have emergent properties. I believe this is one of the single most important traits or qualities of language models. And what emergent properties mean is that an ability is emergent if it is not present in smaller models, but it is present in larger models. And this is a beautiful result because let's take one of these arithmetic performance on arithmetic tasks. On the x-axis, it's the compute power. So you can equate this to the size of the model. And you see, if the size of the model is small, its accuracy on arithmetic is not that great, but suddenly it shoots up. So there is a tip-off point or there is a tipping point over here. After this tipping point, the language model has suddenly become better at arithmetic. And such tipping point is usually seen for translation tasks, for word unscrambling tasks, for question answer tasks. For a huge range of tasks, language models show emergent properties or tipping points, which are directly related to their size. So this means that the reason we increase size is because suddenly the language model starts doing certain tasks which it did not do before. And this is absolutely incredible if you think about it. I don't think anyone still knows why these magical properties arise at certain tipping points, but they do. And this is one reason why people started pushing for size of large language models, because we don't know what's the next emergent property, right? Right now, I told you we are at 1 trillion. We are at 1 trillion parameters, but researchers at Anthropic, OpenAI, DeepSeek, they might be thinking, what if some new emergent property unlocks at 10 trillion parameters? What if another emergent property unlocks at 100 trillion parameters? So big companies are still pushing along or across the size dimension, although it has significantly plateaued a bit. This push for size of language models has significantly decreased now because of small language models and several other things which we won't get into in this lecture, such as test time scaling and some other concepts. But for now, just keep in mind that this emergent properties is one magical thing which LLMs have. And as their size increases, they just get better at doing things. The second thing which I want to tell you about is a lot more intuitive, and I wish someone in the chat would have pointed this out, right? Let me ask once more. What we are doing when we are building an LLM is that, as I told you before, they predict the next token, right? Then how is it that they get so much better at all of the tasks such as translation task, let's say summarization tasks? There are so many other things which an LLM can do. It can understand the sentiment of the language. So if we are just constructing this model to predict the next token, how can a large language model do all of these other tasks? Yeah, how can it understand the language? So someone is saying you have to fine tune. I'll come to that later, but I'm just training the model to predict the next token. So let's think about this again from first principles, right? There is another thing which is so interesting here, and this was recently covered by an OpenAI researcher at a talk which they gave at MIT. And the intuitive explanation for why LLMs need to be so large is because we train them to predict the next token. That's fine. But what language models discover on their own is that the simplest way to learn how to predict the next token, the simplest way to learn how to predict the next token is to learn the language itself. So what's very incredible about language models is that we don't teach language to these models. They learn about it on their own. So for example, let's say there is a sentence, Mary kicked the ball. There is a certain ordering to the sentence, right? There is subject, verb, and object. There are certain rules which languages have. Subject needs to come before verb, before object. This also differs across languages. We don't teach this to the LLM at all, but the LLM learns it. The LLM will never give you a sentence which is opposite of this. And I believe the reason they are learning a language is because we train the LLMs to predict the next token, but LLMs themselves figure out that for me to predict the next token, the fastest way for me to do this is if I learn the language itself. So LLMs need to be very large because they are learning a language, and learning a language is not easy at all. It involves two things. It involves understanding the form of the language, and it involves understanding meaning of the language. So by form, I mean grammatical construction. As we train them on the next token, they realize that they have their own patterns which are forming in their mind. Or when I say mind, I mean some parameters. And they understand the grammatical form. And when I say meaning, LLMs also probably have certain knowledge about the world. So for example, let's say this sentence, blue electrons eat fish. This sentence is grammatically correct. Blue electrons eat fish is grammatically correct, but it has no meaning. So large language models will never give you this sentence because they know this sentence does not make sense any sense at all. So in a sense, large language models understand the form as a consequence or as a byproduct really of trying to predict the next token. And they also seem to have some notion of what's the world in which they are living in. Now, this second thing is highly debated because some researchers believe that language models don't have a worldview. Uh, but learning a language is not an easy thing to do. And that's why LLMs need to have so many parameters. So look at humans, right? How do we learn language? Let's say there are also two theories for this. One theory is that when we are born, we already have a cortex, which further improves as we listen to our parents, etc. Whereas the second theory is that we have no cortex and everything is learned from scratch. So if a large language model is to learn a language, that's the reason it needs to have maybe billions of parameters. Otherwise, it's very difficult for them to learn a language itself. So through large amount of data, we have a huge amount of data initially, and we train the language model to predict the next token. And while doing so, language models understand the form and the meaning of language itself. Now, there is another aspect to this called fine tuning, which we'll come to a bit later. But I hope all of you have some understanding of why do we need so many parameters. The first reason for this is, of course, we can unlock emergent behaviors in language models. And the second reason is because learning a language is not easy. And in this case, a model learns all the languages in the world, right, based on the data which are fed into it. So this is the intuitive explanation. For those of you who like to have intuitive explanations, this second explanation might work well. But for those of you who prefer more technical explanations, the first explanation works well. In any case, my task is to give you all kind of explanations so that you can decide which one resonates with you the best. So these are emergent properties of language models. And one more thing which I want to mention over here is that language models, right, are a bit different than earlier natural language processing models. So earlier, before language model came into picture or the transformer architecture really, we had natural language processing, right? Here also using an NLP model, we could do translation tasks, summarization tasks, grammar checking, etc. But we needed a separate model to do each of these. We needed a separate model for translation, a separate model for summarization, a separate model for grammar checking. The cool thing about language models is that just one model, which is trained to predict the next token, suddenly becomes good at translation, summarization, sentiment analysis, all of these things. Even without fine tuning, we can take the language model to a stage where just predicting the next token makes it better at these tasks. Fine tuning pushes it to the next level, of course. Uh, okay. So, there is a secret sauce which I keep talking about, right? And that's transformers. We are not going to cover transformers in this bootcamp because that gets into theory of how to construct a language model from scratch. So we are not going to get into the transformer architecture right now, but this figure here and the whole, if you dissect this figure, there is something called attention here. So the simplest way to explain attention is different words in a sentence, know what other words mean. And that helps us understand the context of sequences better, context of data better. That helps in predicting next tokens or next words. So all of this must be seeming a bit magical to you right now if you don't know transformers. But in this course, I'm not going to teach you transformers because as long as you have an understanding of large language models, that is good enough for understanding agents. What I want you to appreciate after this lecture is that language models can do wide range of tasks. What are language models and how to construct language models, which is going to be the next section. But before that, I just want to have a small Q&A kind of a section where so I've made four buckets here, right? One, two, three, four. And I know many people are confused between these four terminologies, language models, generative AI, deep learning, and machine learning. So can you tell me what is number one, number two, number three, and number four? So four is the broadest terminology, three is a subset of four, two is a subset of three, and one is the subset of two. So let's start with 4. What is 4 among these? So 4 is actually machine learning. That's the broadest space. Within that comes deep learning, which involves gradient descent and neural networks. Within that comes generative AI, where we have multiple modalities such as vision, text, etc. And within generative AI, the further subset of generative AI are language models. That's the uh, narrowest criteria here. So what we are studying right now is a subset of generative AI, which is a subset of deep learning, which is a subset of ML. And the superset of all of this is artificial intelligence, or AI rather. So I just wanted to clarify this right at the start so that there are no confusions with respect to terminology. Now let's get to how to build language models in the first place, the entire pipeline or the process of building a language model. So let's just throw around some ideas here. Imagine that you are the first team of GPT. So let's say you're building GPT from scratch. What all things would you need? What would you do? So I just tell you that until now we have seen that LLM is a model which takes in a sequence of words, and it predicts the next token, right? This is what we have seen until now. And we have also seen that they have something called emergent properties, and they learn the form and meaning as a byproduct of trying to predict the next token. But now we'll look into how is this built in the first place? How is this constructed? What all will we need as toolkits? Uh, so it's fine if you just throw around some ideas over here. So the first thing which we'll need, of course, is data, right? That's the first thing which we definitely have to start with. And if you look at, let me see if there are so many other answers. So tokenizing encoder. So if you try to keep it a bit broad right now, we first need to start with data, right? And then we need to think about the model itself. So first let's look at the data. So the process of assembling any language model is first you aggregate a huge amount of data from the internet. So for example, here is the data sets which were used by GPT-2 for their training. And when I say GPT-2, it's this paper. Language models are unsupervised multitask learners. For this paper, they use this data. So Common Crawl, Web Text 2, books, Wikipedia articles, etc. And if you don't know what Common Crawl is, or if you're not aware of Common Crawl, it's this open repository of web crawl data, which consists of huge amount of aggregated data from Reddit threads, etc. There is another open web text. So open web text corpus is one more such corpus which is extremely famous where you can get data from. Essentially, you just source data from a huge variety of different links and websites, and that makes up your data set. So that's the first stage. You collect data, and this data can be internet text, books, media, research articles, etc. Wide range of data, and entire books are used. So the whole whatever books are available can directly be used as raw unlabeled data. So this can actually be trillions of words. The scale which we are talking about is huge amounts of data, right? So if you think of one token as one word, look at the amount of words in these data sets. It's huge. So we cannot comprehend the scale at which this is done. Then the next step is that we have to construct a model. So once we have the data is then pass to a model. And for now, when you think of the model, just think of some architecture like this. It's fine if you don't know every building block of this architecture. But for now, just think of when I say a foundational model is essentially a model which is built on the transformer architecture. So you train this model on such a huge amount of data, and the trained model which comes out of this is called as foundational model. This is a very important terminology because a foundational model is a model which has not undergone any additional fine tuning. It's a model which is pre-trained on underlying data. And then on top of that, so this is step number two. Step number one is accumulating the data. Step number two is pre-training the LLM. And step number three is fine-tuning the LLM on labeled data. So it turns out that if you just pre-train the LLM, it's not very good at following instructions. So you need to give a certain set of instructions. Let's say if you want it to be better at translation, if you want the LLM to be better at summarization or classification, you can give certain sentences as or certain input output pairs as labeled data to the LLM, and you can fine tune the language model. So the first data set for the pre-training part, that's unlabeled data, whereas the second data set is labeled. So in the second data, you also provide what should be the correct answer. Here's the input, what should be the translated output. So this is the general, very high level workflow of how LLMs are built. And here I've just put that on text. You train on a large corpus of data. That's the first thing. The first training stage of an LLM is also called as a pre-training. And after the pre-trained or after obtaining the pre-trained LLM, we can further train the language model on labeled data, and that's called fine-tuning. So when GPT 3.5 actually came out into the market, they do all of these three stages. It's not just a pre-trained model, it's a pre-trained model as well as a fine-tuned model. Only then it's released as a product. So all of us interacted with GPT 3.5, I believe in 2022 and 2023. That's a model which is pre-trained as well as it's fine-tuned. So both of these steps need to be done. And the pre-training cost is huge. It's upwards of multiple, or just for GPT-3 pre-training, it costs around $4.6 million. For GPT-4 and for models which have more number of parameters, it will cost even more. So pre-training foundational models is currently done by labs and startups which have that level of funding and that level of vision. So this is the workflow of how an LLM is built from scratch in the first place. And if you see, nowhere in this entire workflow do we teach the language model about grammar. Nowhere in this entire workflow we teach the language model about meaning. It just gets it from the amount of data on which it is trained on. So this LLM, which is pre-trained and fine-tuned, that LLM then serves as the brain for an agent. And why does it serve as the brain for the agents? It's because this LLM, which is pre-trained and fine-tuned, is now extremely good at all kinds of text-related tasks. It's great at summarization. It's great at classification, let's say classifying the text, sentiment analysis, then translation, all various sorts of things, right? So in the previous class, when we took a look at the different types of agents, right, and the tasks which they need to perform, all these type of tasks involve dealing with language. So we need some sort of a model which is good at understanding language, processing language, and that model is a large language model. So let me just pause here for a while and ask here if anyone has any doubts or any questions. So let me take some questions in the chat. Uh, you can keep asking questions if you feel it's important enough. If web scraping is the source to knowledge, and nowadays everyone uses chat GPT. Yeah, so one more thing is that as we are interacting with the LLMs, right, that itself can serve as the data for further training. And I think some of you are also interested in what actually happens in the training procedure, right? So in the training procedure, let me break it down a bit. What really happens? And those of you who are not interested in this or who think it's a bit complex, don't worry about this, but I'm just showing the whole workflow. Let's say if you have huge amounts of data, right? For the sake of simplicity, let's assume we have to build a Harry Potter specific LLM. We have to build a Harry Potter specific LLM which understands and can answer all questions related to Harry Potter, right? So what we'll do first is that we'll source Harry Potter data. Let's say I take this PDF just as a reference, and I use this data and I collect it, right? Once we have all of this data, then what we are going to do is that this data which we have, that's tokenized. By tokenization, I mean it's broken down into smaller and smaller parts. And then each of these tokens pass through the entire LLM architecture. And the LLM architecture consists of the attention layer. There are many layers which are stacked together, the normalization layer, and then there is an output layer, let's say. So you can think of this block as the LLM architecture block. And then what comes out of this is the next token prediction. So this is the predicted next token. And then we compare with the actual next token. So we have the predicted next token and the actual next token. There is a loss term which is calculated between these. That's the categorical cross entropy loss. And then we do back propagation. So then we do back propagation to minimize this loss. And what this means is that, let's say there are 175 billion parameters in this model. All of these parameters are optimized during back propagation so that the next tokens are predicted correctly. That's the entire, so when I say pre-training, it's this entire workflow which happens. So if any of you are actually interested in this, right, then this build LLM from scratch playlist which I have, it's this one. This playlist has 43 videos which teach you exactly this workflow which I right now showed. So my main purpose in today's lecture was to give you a high level overview of what large language models are, so that when we use the term LLMs in future lectures, you know exactly what I mean. But if any one of you want to dive deeper into this and actually know how LLMs are pre-trained, then you will need to spend a significantly more amount of time understanding this. Uh, so there is a question, 175 billion parameters. What are these parameters? These parameters are actually all kind of neural network layers. Then if you have queries, keys, values, matrices, there are several places at which these parameters are present. The simplest way to think about it is y equal to ax plus b, right? Here a and b are parameters. So here the input data, let's say, is your x, and the next token is y. All of these parameters which come in between x and y, those are your 175 billion trainable parameters. Um, there is a question that are agents built on top of generative AI or ML layers? That's an interesting question. So see, now the reason we covered this is because if you see, uh, yeah. So let's say the same example of trip planning, right? And what we want to do is that, let's say on day number 1, we are going to Barcelona. And I want to decide where we are going to on day number 2. We need a model which can understand what is mentioned on websites. We need a model which can calculate distances. So it needs to have access to certain tools, and it should essentially understand what's written on web pages. So there has to be a language layer. So you asked about machine learning, right? The reason why agents use a language modeling layer is because all these other, so if you consider deep learning, right? Deep learning is a very vast field which also has many things that have nothing to do with language. But agents are specifically built on top of large language models because language is the thing which helps you to reason and to plan. So if we look at this definition of agents, right? This definition of agents can plan and take decisions. How is this possible? How will they be able to plan and take decisions if they don't understand what's written on web pages, if they don't understand what's written on booking websites, if they don't understand human feedback. So as a human, let's say if you're given feedback through voice or text, the agent needs to understand what's your feedback, right? Uh, they cannot do all of these things unless they have a language layer underneath. So that's why we say that the brain or foundation of an agent is a large language model. And now when you say large language model, don't just think of Chat GPT. People who have not understood LLMs just associate LLMs with Chat GPT. But when I show you this figure and when I say uh, brain or foundation of an agent is a large language model, right? I specifically mean language models which are pre-trained and fine-tuned. And when I say pre-trained, it means that whole workflow of tokenization, predicting the next token, etc., and then fine-tune. And when you think of LLMs, you should know that they are trained to predict the next token, but as a byproduct, they have become very good at understanding form of the language. They have also understood meaning of the language. And as a result, they are able to draft emails, they are able to understand the sentiment of a given piece of paragraph or a given piece of text, etc. So this lecture is kind of like peeking behind the curtain and really trying to understand what LLMs are. In fact, in our live course, Build Large Language Models from Scratch, this is our first lecture, or rather the first two lectures. That's a 25 lecture course. But in this lecture, I always like to give this because here we teach things from first principles. Actually, one more book which I would like to share with all of you is by Wolfram, and it's called How ChatGPT Works. It's one of the best books I've read on how GPT works. And in fact, um, so let me share this book. This is that book. It's freely available, and I really encourage all of you to read this book because it's absolutely incredible. So some of the ideas which I've got at the start of this lecture, right? Like more options than the number of particles in the universe, etc. It's been inspired from this book. It's just 79 pages and it's a 2 hour read, but it really breaks down what ChatGPT is from first principles. I think that if all of you have this knowledge, you will just get better at building agents and understanding agents. Okay, let's see. So I can take a few more questions now from the chat. Parameters are basically weights and biases. Yeah, that's correct. But they show up at various places. How come DeepSeek with 13 billion parameters perform as good as 175 billion GPT model? What other factors are involved in the performance? That's actually a very complicated question because the answer to that would require. Uh, so essentially, the reason DeepSeek is so good is because they have several things. So first, they have KV cache optimizations. They have something called multi-head latent attention. They have rotary positional encodings integrated with latent attention. All of these things are there. So I won't get into this right now, but the short answer is that they have implemented a lot of architectural innovations, actually. That's what makes DeepSeek so much better. So there is a question on small language models, right? That's actually an interesting question because let me try to explain my thinking about the way the LLM space has evolved, right? So there was a scaling law at the start. There was a scaling law, and everyone was interested in this. That the more you parameters you have, the more better you get. Slowly started reaching a plateau. Then what happened is that businesses started figuring out that if I have a specific use case, I don't need the all the data in the world to train my language model. I will start with a small amount of data. I will start with a small amount of data and I will use a language model which has only 10 to 50 million parameters. And then they figured out that even such a small model leads to great results if you have specific small amount of data. These language models, which are much smaller than their larger counterparts, are called as small language models. And small language models are extremely effective in enterprises. The reason is because enterprises generally want their own corporate brain. So they cannot use ChatGPT. They want to train a language model which has knowledge about their company. about their data, and they have specific operations which need to be performed. So small language models are the future in that space, I believe. If any one of you is further interested, uh, you can watch this 3-hour workshop. Yeah, so this is how to build a small language model from scratch. So I have recorded
That's
this.
it, everyone. Good job.
I recorded this 3-hour workshop 3 weeks back. But before doing that, I really encourage you to watch this playlist because this starts at slightly higher level, but it teaches you how to build an SLM from scratch actually. Um, okay, let's see what other questions are there. Moore's law, yeah, you can think of scaling law as slightly similar to Moore's law, just in the reverse direction. How much math is required? So for this agents bootcamp in particular, I'll try to cover everything from first principles. So I'll tell you the plan going forward. Until now, we have covered the introductory lectures, right, which are LLMs and LLM agent. In the next lecture, what we are going to do is that we are going to see how an agent works. And we are going to write our first code in the next lecture for building an agent. And there, what we'll do is that we'll peek into the inner workings of an AI agent actually. Because when I say that agents have large language model as their brain, you might be thinking, what does this exactly mean, right? You might have understood what LLMs are, but you would not currently see the integration of an LLM into an agent. For that, we'll need to understand something called as the React framework. So React framework, I shared this paper actually in the previous lecture. If you saw, but yeah, this is that paper. We'll need to understand this. In this paper, we'll actually learn how language models are integrated with agents, or how language models can be equipped to plan and reason. So there is something called reasoning and acting, which is React, which we'll be looking at in the next lecture. Okay, so next lecture, now this lecture has come to an end. What I'm going to do is that next lecture will be held tomorrow, which is Tuesday. And in the next lecture, we are going to cover how an AI agent works. We are going to cover this React framework. We are actually going to see our first agent in code. Now, for the rest of this lecture series, it's very important that all of you are regularly going to be attending lectures. You should have an OpenAI API key. So that is the purpose of this. And mostly what I'll be trying to do is that many of the lectures I've constructed with open source LLMs, but a huge number of participants in this call are industry professionals. At least those participants who are from enterprises, you need API keys. For students, I would say go ahead with free API keys. But people who are joining from enterprises or people who are industry professionals, you definitely need to have your OpenAI API key. So that's going to be extremely important moving forward. All other API keys which we'll create will be free. So we need API keys for several other platforms like Hugging Face. We'll need API keys for LLM and agent monitoring platforms. Those are free. But please have them ready so that you can follow along the different coding lectures which we are going to conduct. Tomorrow's lecture will also have coding in Google Colab. So make sure that you have Colab. We don't need any pro plan subscription, but don't join tomorrow's lecture from mobile phone. And let me iterate this once more. Tomorrow's lecture will deal with some code. So many of you who might be joining through mobile phones, please don't do that, because then it's not the best effective medium for understanding. It's very difficult to run code files on phone. Um, so just make sure to avoid that. Tomorrow's lecture, you need Google Colab. OpenAI API key might not be needed in tomorrow's lecture, but it will be needed in one of the subsequent lectures. But just have it ready tomorrow also. Also, people who are on the pro plan, you will receive three things after every lecture. You will receive the Substack, you will receive the notes, and assignments. So I've shared the first assignment with all of you on Discord, right? So it's important that you do that assignment and submit the solution on the Discord group itself. And plus, after each lecture, you may have certain doubts, right? So those doubts you can ask on Discord and I'll clarify them. To summarize the key takeaways from today's lecture, here is what you should take away from today's lecture. First, language models are next token prediction engines. Language models are next token prediction engines, and they are not deterministic prediction engines, but they are probabilistic. So they have a certain confidence score of what the next token should be, and they choose the next token with the highest confidence or the highest probability of being the next token. Now, while we pre-train a language model for predicting the next token, they learn the language itself as a byproduct, which is the form and the meaning of the language. And language models are called large language models because they have huge number of parameters. And why do they have huge number of parameters? First is because they get emergent properties. As we increase the parameter size, language models magically start becoming better at new tasks. Second reason is that as kids, uh, certain neuronal connections are formed in our minds as we learn a language. Similarly, for a language model, learning a language is not easy. That's why they need so many parameters which are flexible, which can be tweaked so that they can effectively learn a language. Then we saw that the core of language models is, of course, this transformer architecture. And we saw the difference between LLMs, generative AI, deep learning, and machine learning. And finally, we saw that when we look at LLMs or any large language model which we are going to use, it has two stages. It has pre-training and fine-tuning. Fine-tuning comes after pre-training. The reason it's called pre-trained LLMs, it's a bit misleading because we already trained it before. The reason it's called pre-trained is because there is also one more stage, which is the fine-tuning stage, which is going to come afterwards. So it's in the anticipation of the next stage, which is going to come. That's why it's called pre-training. I also shared this Google Colab notebook with all of you. Those of you who are students, just replace the models with Gemini models and use free API keys. But industry professionals and people joining from enterprises, please have your API key ready so that we can do tomorrow's lecture efficiently. We'll need to create accounts on many different things, and I'll do that on the go. So you'll need an account on Hugging Face. So just make sure that you have an account which is created on Hugging Face. If you don't have it right now, it's fine. I'll take you through it as we are going through the lecture. Then what else? I might be forgetting some things, but I'll cover it as and when we go through that particular lecture. And then finally, I hope many of you will now start making the link between lecture number 1 and lecture number 2. In lecture number 1, I talked about this foundational layer of agents, right, which is a language model. And in lecture number 2, we have seen what that foundational layer is. And I hope you think beyond ChatGPT when you think of a language model. Try to think from first principles. Like, here is how I relate it to physics, right? Because physics is what comes naturally to me. So I look at physical models and then I try to relate to language models. I think that's always a better way to learn rather than learning just directly from applications. Okay, so now that we know agents and LLMs independently, I will look forward to seeing all of you in the next lecture, in which we'll learn how agents actually work and the React framework in particular. And again, let me repeat one more thing. If any of you is actually interested in going deep, make notes along as you are learning. Because one thing which I have learned myself is that as I make notes, I get better at the material. Second thing which I've learned is what I also covered in the Discord group assignments is teaching, the benefit of teaching. So when I say teaching, what I mean is that if you really have understood something, you should be able to teach it to someone who has no clue about that topic. And if you're not able to teach it, it means you have not understood it. That's why I started explaining LLMs from very simple terms. So if you want to teach, let's say, language models to a 10-year-old, how will you teach? You cannot use difficult words, right? So that's one of the best ways to teach, or best ways to learn rather. So I call this learn by teaching. And I don't know why this method is not implemented in universities, right? In all of our college, during undergraduate, graduate, I gave exams and they judged me for my marks. But instead, if there were teaching assignments, so if there was an exam where you teach your students and we check how well the students have understood it, I think that's a better indicator of whether you have actually learned the concept or not. So as an exercise, try explaining language models to someone who has no clue about this field. And if you are able to explain it successfully, then maybe you have understood it well. Thanks everyone. I will look forward to seeing you in the next lecture, which will be at the same time, 2 p.m. tomorrow, same Zoom link. So I look forward to seeing you then. Thanks everyone. Bye.